Hello and welcome to Eng Phys 2P04 Lecture 19, Shear, Stress, and Strain. Now we're going to be looking at the deformations resulting from applying shear forces. So if we take a shear force, which is a force parallel to a surface, rather than perpendicular to it, the normal or axial force we were looking at before, then this is going to try and slide planes parallel to each other so that we get this gamma here called the shear strain. Shear strain defined as the change in kind of plane position per unit plane separation, so delta x over Ly, which is the x displacement per y length. Now we can define this the same with kind of an analogous definition that we use to the axial stress. So shear stress is force divided by Ay. Tau yx means the shear stress on the y face in the x direction, and the y face means the face perpendicular to y. So imagine that there's like x going horizontally, y vertically, and z is out of the page here. Then this tau yx would be up here in the x direction. And we've also got that looking at the angle here. So this angle in radians really is the shear strain. Shear strain is typically very small, and so the angle is equal to its own tangent. Try that out for some small number when gamma is in radians, and you'll see that tangent of an angle is equal to the angle as long as the angle is smaller than about like 0.1. This is a pretty good approximation. Then we've got that, and we know that the tangent is equal to opposite over adjacent. So tan of gamma is delta x over L, and so that's the shear strain. We've got the shear stress that's produced by this force on this top surface leads to this kind of shear strain. And how are the two related? So how much shear strain do you actually get? Well, that's determined by the shear modulus, G. So the shear stress gives you G times the shear strain. This is entirely analogous to what we were doing with axial stress and strain. The perpendicular force over a face is defined as the axial stress, and we know that that's equal to Young's modulus times the axial strain, where axial strain was the change in length per unit length. And the parallel force over the area is equal to the shear stress, which is equal to the shear modulus times the shear strain. And we're even using like G and gamma and E and epsilon for these things to try and be similar. Also, this is like sigma. It's kind of like sigma tau, like an ST. It's sort of the next letter. Then, okay, so G gamma is equal to the change in position per unit length. Not so much change in length per unit length, change in position per unit length. In terms of our displacements, the axial strain was equal to the for small numbers, it was equal to the rate of change of the x displacement with respect to x. And so the shear strain is just the rate of change of the y displacement with respect to x, or the way we've shown it here, the x displacement with respect to y. So notice that these two forces by themselves would create a couple, so this isn't in static equilibrium. If we want to balance it out, we need to either apply a moment, or we can put this into pure shear by applying a complementary pair of forces on the opposite faces so that they're the same force. This is no longer creating a couple. We've got, as long as they're displaced by the same amount. If the shear strain is actually very small, then we can ignore the fact that this, the distance perpendicular between these two forces is not necessarily the same as this if it was originally a square. So let's say that the shear strain is pretty small so that doesn't come into play. And then this is in pure shear. So we've got that the shear stress on each face is equal. Distances here are exaggerated. Now let's look at an infinitesimal cube. If you want to look at a really small geometry of this, like imagine we're taking like an original cube and we're going to look at a really small kind of differential cube or differential rectangle in general inside the material. Now we've got a picture here which defines all of the shear stresses in different directions. So tau yx would be on the y face in the x direction. Tau zy is on the z face in the y direction. So here on this picture, the x-axis is this way, y-axis is that way, and the z-axis is up. Now, for this tiny cube, because it's really small, the stresses are going to be continuous. So if you go to a small enough size, then the stress can't change instantly, which means that the normal stress on like this side of the cube is the same as the normal stress on the other side of the cube. It's going to be very similar to the normal stress on the other side of the cube. So that means, and it's the same on the other side if it's in static equilibrium. And so that means that the normal stresses, the axial stresses, the sigmas here, can't create any moments, because if the stress on this side is basically the same as on this side, and the distances are kind of small, right? So then we've got like a tiny change in sigma over that distance is not going to really create any kind of moment. So we can't, the only way we can have moments on this is if the shear stresses are not balanced. So if we've got like a tau yz up on this side and a tau yz down on the other side so that it's not creating a net force from shear, then we've got to have a complementary tau zy on the opposite, on the complementary faces here to cancel that out. So here we said we could create another couple by adding these shear forces on the other sides to cancel this out, but microscopically that's the only option. So it turns out that the shear stress is symmetric. Tau xy equals tau yx. Let's do an example, pure shear 10 centimeter cube. So we're going to take a 10 centimeter cube that has one face, the bottom face here, glued to a table and put it into pure shear by shear stresses on the xy faces given by this. So Fyx equals 10 newtons equals Fxy, meaning that the forces in this picture, with the distance here really exaggerated, are all equal to 10 newtons. If the cube is made of plastic with these parameters, determine the shear stress, shear strain, and the lateral distance the top face of the cube is going to displace relative to the bottom face. So determine delta x, that is. So here they've given us Young's modulus and Poisson ratio, but they haven't given us what we really need, which is the shear modulus. However, as long as it's an isotropic material, which is pretty likely if it's plastic. Typically, plastics are kind of like an amorphous blob of all kinds of polymers, just sort of globbed together without a particular structure. Let's assume that anyway for this. Then what we've got is that the shear modulus is the isotropic case. So for an isotropic material, one that's the same in all directions, then the shear modulus is just the Young's modulus divided by 2 times 1 plus Poisson's ratio. Okay, so the stress is just the force divided by the area. Since the force is parallel to the surface, it's a shear force and then a shear stress. So we get 1 kilopascal. And the strain is just the stress divided by the shear modulus. Shear modulus is a gigapascal over 2.8. So the shear strain is 2.8 E minus 6, and that's in radians. This is pretty small, so we can use the small angle approximation, which tells us that delta x is just Ly times the shear strain. So in this case, 280 nanometers. Think about this for a moment. You've got a reasonable force, so a 10 Newton force, that's about the weight of 1 kilogram, applied to a 10 centimeter cube that's made of a pretty reasonable plastic. And how much does the top face move in result because of that from shear stress? Only 280 nanometers. So shear stress is shear strain is not a huge amount of strain. How does this compare with axial strain? Well, it's actually a bit bigger. So here like magic, I've done this calculation now, and you find that the axial strain you would get if you were to apply the same force in the direction of the face is 2.8 times smaller than we got for shear in this case. So that's what are we to take away from this? Well, it's that reasonable forces for reasonable material actually does very little to deform solids. If you want to have massive amounts of deformations, like most of the time solids that are pretty strong solids will hold up to the things that you're doing to them. If you but we still need to be able to calculate how they're going to behave in response to very large forces and very large stresses, and that's when we're going to have large deformations. Shear strain details, engineering strain, and true strain. Strictly speaking, the shear we've been talking about is engineering strain. There's another definition, which is the true strain. So consider this arbitrary deformation of the material where A goes to little a, B goes to little b, etc. for C and D. We've got the displacement of it is written as U subscript X and U subscript Y. And so the deformation can depend on which part in this differentially sized material we're looking at. So we've got a deformation of a displacement of point A, which is not going to be the same as the displacement of point B, C, and D. So the cube is not just moving, but it's, or the square rather, is not moving, it's also deforming. Now, the point A moves from its original coordinates at xy, this is, let's call that xy, to this new set of coordinates, whatever it was, x and y, plus ux and uy at the original xy. So this is ux at xy and uy at xy, the motion of the cube, how far each part of it has moved. Okay, so uy at xy is actually shown here from the bottom. This would be uy at x and y plus dy. How much the top face of it has moved. Okay, at the left end. What about the top face at the right end? So how much has d moved in the y direction? Well, that would be uy at d's coordinates, and d's coordinates are x plus dx and y plus dy. So d has moved in the y direction from y plus dy to y plus dy plus the y displacement at its original coordinates, x plus dx, y plus dy. Okay, anyway, what's the point of all this? Well, the point is just to be able to define what strain is. So true strain is epsilon ij is the rate of change of ui with respect to coordinate j. So for instance, epsilon xx would be the rate of change of the x displacement with respect to x, and the shear strain, true shear strain, epsilon yx, for instance, would be the rate of change of the x displacement in the y direction. So the alpha here, you can see, is equal to del uy by del x times dx. And since the bottom side of this triangle, or bottom side of this, is equal to dx, it was the original width of this, then alpha, the angle, is equal to this, del uy by del x, whereas beta is equal to del ux by del y. So these components here are the shear strains. Now before, what was our shear strain defined as? Our shear strain was defined as the total angle change between this face and the perpendicular face. Now we've defined each of these shear strains as kind of half of that angle change. So compared to the what we were dealing with before, the engineering strain, that was defined as the total angle change. Okay, so the total angle change, engineering strain, the half angle change is the true, as it's called, true shear strain. So engineering shear strain, twice the true shear strain. In the axial case, though, it turned out exactly the same. If you want to look into the math of how that worked out, besides just taking in these definitions, then the math is here for you. I've done that, so feel free to go ahead and read through that if you like. So let's summarize what we need to know here. For isotropic materials, which are ones that behave the same in all directions, we've learned that axial stresses and strains are related through the compliance matrix. So here's our axial strains, axial stresses, and there's our compliance matrix. And themselves are defined as these. Epsilon I is the rate of change of the displacement in the I direction with respect to the I direction. So the x strain is del ux with respect to x. And the shear stress now and true shear strain are related through the shear modulus. So epsilon yz is equal to 1 over 2g, tau yz, etc. for the other coordinates. Where the shear modulus, at least for an isotropic material, is E over 2 times 1 plus nu, and the engineering shear strain is the sum of the complementary true shear strains. So it's equal to the true shear strain over 2. You can write both via the stiffness rather than compliance coefficient. So if you want to write it in terms of stress equals something times strain, then this is the something for the axial components. And for shear, it's really a lot easier. It's just one constant. So even though shear seems like a complicated thing to describe and it's multi-dimensional, like we've got tau yx, you have to remember that's on the y face in the x direction, and it's a little bit more difficult to visualize than the axial terms. Mathematically, it's really a lot easier because it's just a constant and the axes aren't coupled, at least for an isotropic material. Next lecture, we're going to break this symmetry and get into a little bit more complicated things with shear. But at least for now, tau yz is just equal to a constant times gamma yz. All right, so next what we're going to do is program this in FlexPDE. How I'm going to do this is I'm going to show you the code, and you can just copy this out of the notes if you like. I'd like you to take a minute to go through it, and this section is going to talk you through that a little bit, just to figure out where these things are coming from. So first thing is the definition section. We've got we're defining our Poisson ratio here, we're defining Young's modulus, we're defining the shear modulus, and then we're going to make up some constants, C11, 2233, 1, 2 to represent the different terms of these, and imagine like a matrix multiplication where these are our stiffness matrix terms. So C is for stiffness as usual. And then we've got the strain definitions. So the axial ones are just the displacement in x differentiated with respect to x, and similarly for y and z. And then we've got our true shear strain defined here. Kind of like, well, yeah, so EXY. True shear strain really should just be dx of v and then dy of u for the other one. But we're going to assert that microscopically this sum, the whole thing should be symmetrical so that we're not exerting torques on the thing and it's in static equilibrium. All right, so then what's going on is we need to write Hooke's law, right? So we've got that our axial stress is equal to these coefficients, the stiffness coefficients times the strains. And in shear, it's just a lot easier. The stress is equal to 2g times the true shear strain. And then what we do is assert that the whole thing is going to be continuous. So we need to put in this differential equation to assert that the stress and the stresses across the entire material are continuous, right? So the only reason that they would be that they would not be just a constant over one dimension would be if we've got some loading happening internally, and we would apply that on the right hand side later. Like maybe we'd say that this is equal to some kind of a constant, and that would mean we've got some stress continuing to build as we go through the body of the material. We can also apply distributed loads on surfaces with uniform pressures in the boundary section. So then everything I just explained is discussed here in the notes. So if you prefer to read it, then you can go through that in writing. Okay, FlexPDE boundary conditions. Let's look at the boundary conditions now. To actually apply loads to the object, we'd have to use boundary conditions. So for instance, if we wanted to apply a load in the negative z direction, then on the top surface, after we extrude a shape from this, we'll look at an example of how you might draw some shapes soon, and in the tutorial you're going to look at a lot of those. Then we're applying a load in the negative z direction on the top surface of 50e minus 9. So what's interesting is how does it know that this is going to be in pascals? It's kind of interesting. We apply a load on W, and remember what W was. W was the Z displacement. We apply a load on the Z displacement variable in pascals, and that somehow defines a stress. Well, what's interesting, this is a little bit surprising, but where does it actually use? So a value boundary condition just says that U, in this case the X displacement, is 0 on that entire surface. But a load boundary condition does something that you may, that's a little bit surprising. So what this does is it sets up the flux of the variable through that surface. So in this case, the top surface. So the W equation, say, well, actually this is not the, this is the W equation. So dx of sxz over 10, and then syz over 10, sz over 10, is not the same equation as this one. It looks like, okay, well, we're just dividing all the variables by 10, and that's the same equation. So while mathematically these two differential equations are the same, they don't behave the same to a load in response to a load boundary condition. How it works is when FlexPDE solves this, it does so basically by numerically integrating, and then it sets the constant of integration on the surface. As we go across a surface, it's sort of a discontinuity, like what it sets at the boundary is kind of like your constant of integration, and it'll set that equal to what you've set up for your load there. So that's going to be based on the load boundary condition. So this one is going to say for this that we're going to have a Z stress of negative 50 E minus 9 on the top surface after we integrate that, ignoring the shear things. But this one is going to say you'll have a Z stress over 10 equal to 50 E minus 9. So it's going to behave like a 500 gigapascal stress rather than just a 50 gigapascal stress. So that's something to be aware of. If you were to change around the differential equations, then you'll find that the boundary conditions are going to behave a little bit differently. We're going to look at an example and explore this. So example, beam thinning by pulling on it in FlexPDE. Suppose you take a 3 meter by 1 meter by 1 meter steel beam and apply a 200 meganewton force to each end on the long section of the beam. Calculate the deformation of the beam if the beam is otherwise free, and verify the results in FlexPDE. So this is the exact same example as we did, as one of the ones that we did in lecture 18. You can redo the calculation for a little bit of review, or you can just go look up the answers if it's too trivial for you at this point. And then what we're going to do is verify the results using the FlexPDE type code. If you have enough information from what we did in the last little bit of this lecture, then feel free to try and write that FlexPDE code yourself before you jump to the answer. And then what we're going to do is try to rerun it using this different X differential equation and see what happens. So previously we learned that this gives us a displacement of 3 millimeters. Now this is the full FlexPDE program to do this that I used. You just set up your variables, you set up your definitions using the values that we were given here. Now this, a little bit of talk at the beginning. So what does n grid equals 10 do? This just makes it kind of a denser mesh. You're going to need to turn that down if it tells you that there's too many grid points. Then just turn that down to like a 4 or a 5, and it's going to make less dense of a grid. So there's the boundary conditions that we apply. So I've got some comments in here. How we draw this surface is we imagine mapping out a square. So we start at 0, 0, then we increase Lx at the x coordinate to Lx 0. So we go horizontally across, and then we go up to Lx Ly, and then we go back over, and then we go down to 0 Ly, and that maps out the square. And then what we're going to do is on that square, we're going to extrude out a Z surface by setting up this extrusion in this section before. So we name the extrusions here, and then we set up their boundary conditions down here. So we go from Z equals 0 to Z equals Lz. And what's going on all of the faces? So we've got 6 faces. We set up the boundary conditions on the bottom surface here. And what you set up on that bottom line from 0, 0 to LX0 applies on the entire face after you do that extrusion. So there's really 6 faces. We've got the y equals 0 surface, the x equals Lx surface defined here, the y equals Ly surface here, the y equals 0 surface here, and the bottom surface, that's the z equals 0 surface, and the z equals Lz surface, the top surface here. Now, what have we defined? We've defined on the bottom surface, we've got no x force, we've got no y displacement, no z force. On the right surface, we've got a load in x, so we've got an x stress of S applied. We've got no y force or z force. On the back surface, so the y equals Ly surface, we've got, or maybe we'd call this the, depending on how you're viewing the square drawn, on the top surface, and let's imagine z is in and out of the page. On the top surface then, we've got no forces applied. On the, this is actually a typo, on the x equals 0 surface, yeah, there we go, that makes more sense. On the x equals 0 surface, down here, we've got no x displacement, and we've got no stresses in the other dimensions. Okay, and then you can set up some monitors to look at the variables that you're looking for. Then, running this, what I get is the same deformation as before, and after changing the variable, we get in this equation to this equation. You can try that out, and the deformation goes up by a factor of 10, as you would have guessed. So here's our FlexPDE. This is the program I was just showing you there, and running that looks something like this on this computer, and there it is. So we've got the shape there, x this way, y is kind of into the page, and z is kind of up from this particular angle. And you can look at this graph and see that on the right side of the surface for the large x value, we've got a displacement of 3 e minus 2. This is after we've messed up with the differential equations here. And so just proof that it actually does make a difference. If we get rid of that and then try it again, we go back to 3 e minus 3 as our x displacement on the right hand side. Okay, even if you were doing all of the other ones just by watching the videos and not really doing the example, then on this example, it's your chance. This is time. This is your time to finally open up FlexPDE, type in those things, copy them in from the notes, go and download the notes if you haven't gotten them already so you don't have to type all that out, and make these changes. So modify the program that we wrote earlier so that instead of being a rectangular prism, it's a 10 centimeter cube. We're going to redo the pure shear example from the beginning of today. So remember this example here where we found that it moved by 280 nanometers, the top surface there. We're going to redo that using FlexPDE. Doesn't that sound fun? Yeah, of course it is. That's right. Yeah, okay, so let's try that. Give it a shot. Did you get it? Did it work? You don't really need me to tell you the answer. It's 280 nanometers. Here's how you're changing around things in here. You've got to change the definition section. So if you remember to do that, remember to change the applied stress, remember to change the parameters because they were a little bit different, and the sizes. If that was a mistake, then go and fix that and see if your program works now. Next part, we had to change the boundary conditions. And so we'll leave the z's as they were, but we do need to change what's going on in x and y to this. If you do all that, here we go, pure shear. Then it looks like this. Is that what yours looked like? Hopefully not, because this one's all screwed up. Actually, this is the real program. And 2.8 e minus 7 or 280 nanometers. So, don't get discouraged if at first you end up with something going wrong here. It's probably to do with what's going on with your boundary conditions, what size you set things to. If you try and magnify the stress, you may find that meshes are badly folded, and it's showing you the wrong kind of displacement there. So just, double check things, be careful with what you've changed, go back to code that worked, and don't give up.